Okay, so let's start. I'm Bhargav. I'm a PhD student in IISc, and I'm one of the TAs for this course, Foundations of Cryptography. What we'll do is, uh, every Saturday from 4 to 6, we'll have a problem-solving session, in which case we'll solve problems like the problems that you might have, uh, like the problems that you might get in your assignments, and hopefully these problem-solving sessions would help you solve the assignments. So, before we begin, I request that if some of you are not muted, please mute yourself. If you have any questions, then during the session you can unmute yourself and ask. But if you don't have any questions, please mute yourself. Okay, so let's start. Yes, you will get the recording. Okay, so what can you see my screen as well as the slides?
Yes, we can.
Okay, yeah. Okay, so uh, first, okay, people are still joining. Okay, so first let's quickly recall what we did in the last week. So in the last week, we first saw.
Your voice is breaking, sir.
Oh, can you repeat that?
Your voice is breaking.
Okay, just a second.
It's fine, sir. It's fine.
I think it's because people are joining, so I get interrupted every time someone joins. Yeah. Okay. So in this week, we first saw a few things about what cryptography is, what the goals are, and one of the main goal in cryptography is for two people to communicate with each other privately on a public channel. Uh, then we also saw the definitions, limitations, and attack models of symmetric encryption. So, in symmetric encryption, the keys used for encryption and decryption are the same. The limitations of the symmetric encryption model is that the sender and the receiver have to agree upon a key beforehand, and this might be a non-trivial problem. And we also saw some attack models like COA, KPA, CP, and CCA. Now, here I'll just go over what we saw in the last week, and like whenever we solve problems, we will recall all of these in detail whenever we need it. Okay. Then we also saw some historical symmetric ciphers and how to cryptanalyze them. So, for instance, we saw ciphers like the shift cipher, monoalphabetic ciphers, polyalphabetic ciphers, Wigner cipher, and Vernam cipher. We'll also recall some of this while solving the problems. After that, we saw the definition of perfect security. And since we'll use this definition for quite a few problems in this session, let us recall this definition. And if you have any questions about this definition, just ask me now. So, cipher pi, which is a three tuple of the algorithms generate, encrypt, and decrypt, is said to be perfectly secure if for all distributions of the message space and the key space and all message and ciphertext pairs, we have that probability m equals to m given c equals to c is the same as probability m equals m. So what this definition intuitively says is that the ciphertext should not reveal any information about the message. So is this definition clear to everyone? Because we will be using this at a lot of places. Okay, so if it's clear, let's move on. So now, in a lot of ciphers that we use in practice, they can assume without loss of generality that uh, the key would be chosen randomly from the key space. And in fact, even theoretically, we can assume this without loss of generality. So we don't need to worry too much about what the distribution of the key space is, but we do need to take into account the distribution of the message space. After this, we also saw two alternative and equivalent definitions of perfect security, and we also saw a secure encryption scheme called one-time TAP, and also the limitations of perfect security. So uh, now let's move on to the problems that we have for this week. So the first problem is as follows. Which of the following conditions is or are sufficient to get a perfectly secure encryption scheme? And the options are ensure
Sir,
that the, yeah,
sir, in the slides, the thing is not visible. मतलब the question is not there, na?
okay, so I understand the slide is lagging.
Yes, yes. मतलब
Okay, okay.
it,
Uh, Okay, so let me try to reshare my slides.
yeah, yeah. Now it's okay.
Okay, in any way, like, yeah, let me try to reshare my slides. Okay, yeah, so can you see the question now?
Yes, yes, sir.
Okay. Okay, so the question is which of the following conditions is or are sufficient to get a perfectly secure encryption scheme? And the options are ensure that the key generation algorithm outputs a uniformly random key from the key space. Option B is ensure that the encryption algorithm is randomized. Option C is that ensure that the key is as large as the plain text. And option D is none of the above. So would some of you like to answer the question? And this is just a recall
B, sir.
question.
B, sir.
Okay,
And
B
B
for
option go
okay, B or D? B for Bombay or D for Delhi?
B for Bombay.
Okay, why?
C, I think C.
Okay, why? Like, did you see something in the class that makes you think that it is B or C? Okay, so the answer is actually none of the above. It's D. Okay, and the reason why the answer is not B or C is consider this algorithm. Consider this encryption scheme which just does nothing. The algorithm, okay, so it does not use a key at all and just outputs the message padded with some random string. Okay, now the encryption algorithm over here is randomized, but it is still outputting the message as plain text added with some random bits, right? So just because an encryption algorithm is randomized does not mean that the encryption scheme is secure. Okay, so that rules out B. What about C? I mean, consider this encryption scheme in which the size of the key is as large as the plain text. However, what the encryption algorithm does is it does not look at the key at all. It just outputs the message as plain text. So over here, even though the key is as large as the message, the scheme is still not secure. So neither B nor C is sufficient for the scheme to be secure. However, C is a necessary condition for the scheme to be secure. So if the question were which of the following conditions is or are necessary to get a perfectly secure encryption scheme, then the answer C would have been correct. But since the question is which of the following conditions is or are sufficient, the C is also not true. So D is the correct option. Is this fine?
Yes, sir.
Sir, it means B and C both are required, no? Encryption, random encryption algorithm as well as the key, both should
No,
be
no.
available.
Okay, both are okay. Even both combined won't give you uh, a completely secure encryption scheme, and here's the reason why. Consider this scheme where the key is as large as the plain text, and the encryption scheme is also random, but the encryption algorithm does the following. It outputs the message padded with the key and there's some random bits. So even though this satisfies both B and C, the algorithm is still giving you still giving you the message as it is, right? Is this fine?
Sir, which you explained, is it was there in the slide also? Matlab, the explanation for the B and C option.
Okay.
No, no, I'm saying that your slide is not matlab, moving. Na problem
Oh, no, no, no,
one is
no. Okay,
missing.
okay, okay. So
Okay,
these are not in the slides. I was just explaining these orally.
okay, okay, okay.
Okay, yeah. Okay, now now you can see problem 2 on the slides, right? Hello. Okay. So I assume you
It's
can see
visible.
problem. Yes?
It's visible.
Okay, yeah, great. Okay, so the second problem is identify the incorrect statements from the following. The options are a scheme is COA secure if and only if it is KPA secure. A scheme is KPA secure if and only if it is CPA secure. A scheme is CPA secure if and only if it is CCA secure, and none of the above. So, like, we'll discuss what all these four are, but depending, like, would anyone if you like to guess the answer, or would anyone if like to attempt this question?
None of the above.
Okay, so you are saying that all four statements are correct.
Incorrect statement, sir.
Incorrect,
Yeah, okay,
incorrect.
right. So what you are saying is options A, B, and C all are you have to pick all of them, right?
Sir, A.
Okay, okay. So first of all, the question
D,
is
D.
okay. First of all, the question is identify the incorrect statements. Okay, so now tell me which statements you think are incorrect.
A, B, C.
All
Sir,
three.
first,
Okay. Okay, so one of you is saying all three, one of you is saying A. Are those are the only answers? Okay. So if there are no more answers, let me tell you the answers are all three are all A, B, and C are incorrect. And let's see why. Yeah. So first of all, let's recall what all these three are. So recall that COA means COA stands for ciphertext only attack. And over here, the attacker only has access to the ciphertext C and using this compute some function of the underlying message M. So this is what COA is, and this is the weakest attack model. The a slightly stronger attack model is the KPA attack model, and KPA stands for known Okay, here the attacker has the ciphertext C and message ciphertext pairs M1C1 to MKCK, and the goal is to compute some function of M, the underlying message associated with the ciphertext C, but for a C not in this set. Okay, so this is what KPA is, and it's clear that KPA is a stronger model than COA. So it need not be true that if a scheme is COA secure, then it is also KPA secure. I think that was the first option, right? That KPA secure and COA secure are exactly the same. But COA secure is weaker than KPA secure. So just because something is COA secure does not necessarily mean that it's KPA secure. So that rules out option 1. Okay, now let's look at the other two attack models. The third attack model is the CPA model, and this stands for chosen plain text attack. Okay, wait. Yeah. Can you? I think you can see the slides now. Yeah, CPA stands for chosen plain text attack. Here the attacker has ciphertext and again message ciphertext pairs, but for messages M1 to MK of their choice. Okay, so this is the definition of CPA. Now, can someone tell me what is the difference between CPA and KPA? Because if you look at KPA, over here you also message your ciphertext pairs, and in CPA you also message ciphertext pairs. So what's the difference between the two?
Uh, in the second, I think any plain text can be मतलब use ना
Oh,
their
can you repeat?
options
Okay,
Sir, here
attacker's
the
choice.
ciphertext is available of his choice because messages are known to him.
okay. Can you repeat that more slowly? I lost you.
Pardon?
Can you please repeat what you said a little more slowly?
Sir,
I lost you.
actually, in the CPA mode, to M
Okay,
and MK messages which are known to the attacker, he is having the available ciphertext.
okay, but that
But
is also okay.
in the previous one, that the message and ciphertext pairs are available. Okay, that's available, right? In both
I
the
mean,
cases,
right. Message ciphertext
And
pairs are
and
available.
in the first one, the given मतलब encrypted message are given ना मतलब for not the adversary's choice.
Exactly.
Is it
So,
the
right. In the first case, uh, the adversary does have some message ciphertext pairs, but the messages M1 to MK can be arbitrary. in chosen plain text attack, the in chosen plain text attack, the message ciphertext pairs are known to the adversary, and furthermore, the messages M1 to MK are of their choosing. So another way of saying this is the following: the attacker has Oracle access to the encryption algorithm. So basically, they can somehow manage they can somehow get ciphertext for messages of their choosing from the encryption algorithm. And CPA is an even more stronger attack model than KPA. Okay, let me write it. So just because something is KPA secure, that does not necessarily mean that it's also CPA secure. And finally, for CCA, so here the attacker has the ciphertext and Oracle access. Both the encryption algorithm and the decryption algorithm. So in other words, the attacker has for their choice of messages M1 to MK and C prime 1 to C prime. So over here they can not only get ciphertext for their chosen messages, but they can also get plain text for their chosen ciphertexts. And yeah, and again, CCA is an even more stronger attack model than CPA. So just because something is CPA secure does not necessarily mean it's CPA secure. And since options A, B, C said that, like C, so recall the options. The options were that COA is equivalent to KPA, KPA is equivalent to CPA, and CPA is equivalent to KPA. So all three were wrong. Is this fine? Okay, so in that
Yes, sir.
case, yeah, we can move on to the next problem. Okay, so which of great, very big answer. So which of the following is a valid condition for a perfectly secure encryption scheme? Yeah, the options are again someone wants to join. So the options are for all key in the key space, the probability that the key is equal to k is equal to 1 over size of k. That is, the keys are chosen uniformly at random. The second option is for all ciphertext C, for all messages M, probability that C is equal to C given M is equal to M is the same as probability C is equals to C. Uh, Third option is for all ciphertext C at all message pairs M1 and M2, probability that ciphertext is C given message is M1 is the same as the probability that ciphertext is C given the message is M2. And the last option is for all M1 and M2, in all ciphertext C, probability that the message is M1 given ciphertext is C is the same as the probability that message is M2 given ciphertext is C. So this is again just a recall question. So would anyone if you like to attempt this? I anyways showed you the answer extensively.
Is it B and D?
Okay,
C.
B. Yeah, the answer is C. Okay, it would have been B if so it would have been B if B were probability M equals to M given C equals to C is M equals to M. So it would have been B if the roles of M and C were switched. But yeah, it's C, and this is the first equivalent or the first alternative definition of secure, like perfect security, right? With this basically says that the ciphertext does not depend on your message. It's sort of independent of your message. Okay, so if this is fine, we can move on to the next problem. Okay, so the next problem is so which of the following is or are randomized algorithms? The options are the key generation algorithm, the encryption algorithm, or the decryption algorithm, or all of the above. So this is again a recall question. So does anyone want to attempt this?
A and
Sir,
B.
key generation algorithm and encryption algorithm are the randomized.
Okay,
A
so
and B.
A, right.
A and B.
Sir, A and B.
Yeah. So it's A and B. Okay. Okay. And okay, what goes wrong if the decryption algorithm is also randomized?
So
Sir, this
plain
this
message get change.
description.
Original message get change
Sir, it
if
is
we use
deterministic function.
randomized algorithm.
Okay, so two of you were answering. I couldn't hear what either of you said.
It is deterministic function. Description.
Right, yeah, it is a deterministic function, but what I'm asking is what goes wrong if we allow the decryption algorithm to be randomized?
Sir, we
So
will
the
not get
original
the same
message.
message. Original
Again,
message we cannot recover.
again, two of you are
We
answering. So can just one of you say something?
So original message get change, which is sent by the sender if we are using randomized algorithm.
Okay, and why is that the case?
So because if we are using because in the random algorithm, if we are using the same key and the same message, we will get the different encryption algorithm.
Okay, so
But
yeah,
in deterministic, if we are using the different key and different message, but we will get the plain text, same text message.
okay, so yes, you are right. So if our decryption algorithm were randomized, there is a possibility. It's not necessary, but it is possible that depending on the what randomness the decryption algorithm is using, it might output different things. Now, since the output of the decryption algorithm is supposed to be the message, it shouldn't have, its output should always be the same. Its output should not depend on its own randomness, right? That is why that is why we want a decryption algorithm to be a deterministic algorithm. Okay, so now let's look at the next question. Yeah. So the next problem is which of the following is or are publicly known? Again, the first three options are the same. The fourth option is the message. The fifth option is the ciphertext, and the last option is the key. So again, this is a very simple question. Would someone like to answer?
it depends on the model, na?
Okay. Okay. So okay, what is recommended?
Ciphertext, na?
XFTF algorithm.
Okay. Again. Okay. Let me go option by option. Do you think?
The key is available. Key is for publicly known.
Okay, wait. If how can the key be publicly known? Because if the key is publicly known, the key is known to the adversary. In that case, there is no point in encrypting, right? Even if you encrypt using the key, the
X,
adversary would find out.
Sir,
except the
actually,
remaining all can be
Oh, I lost you.
random, I think.
publicly known, except key.
Okay. Again,
Except key
So
remaining
according
can
to
be
the
public.
Kirchhoff principle, key should be private.
okay. All right.
Yes, because public key should be public, na? Because for the encryption.
Okay. So, okay. Let's say right now we are just in the symmetric encryption model. This key used for encryption as well as decryption is the same. There is just one key. There is no public key, there is no private key. There is just one key. In that case, can you reveal the key?
I don't know.
Okay, right. Okay, so let me do one thing. Let me go over this option by option. Do you think A is publicly known?
No.
Okay, what about B?
No. Yes.
C?
Yes, yes, B.
Yes, it knows.
Okay, so there. Okay. Yeah, this is getting messy. Let me just tell you the answer and then explain. So it is recommended to make both A, B, and C publicly known, and ciphertext is also publicly known because it's sent over a public channel, right? Message and key should be private. Because if message is public, there is no point in encrypting. Everyone knows the message. And if key is public, and we are in the symmetric encryption model, again, the adversary can decrypt the message, right? So there is no point in encrypting again. So is this fine?
Yes, sir.
Yeah.
So it means na the working should be known. मतलब generate how
Right.
it generates and na encryption and
Right.
decryption should be known.
Right.
But yeah.
So all the algorithms should be known, but when you instantiate the algorithm, you get a key. That should not be known. Yeah, so the algorithm should be public. And that's so that the statement that the algorithm should be public has a name. Can anyone tell you what that can anyone tell me what that name is? It's a principle.
Kirchhoff principle.
Yes, right. Okay, so the next problem is the following. Consider a variant. Again, someone wants to join. So consider a variant of the one-time paired encryption scheme where instead of using the XOR of message and key bits, the ciphertext is obtained by using the AND of the message and the key bit. That is, if message is M1 to Mn and key is K1 to Kn, and the ciphertext C equals to C1 to Cn is obtained by as follows. For all I in N, the ith bit of the ciphertext Ci equals to Mi and Ki. Okay. So the question is this version of one-time pad also perfectly secure? The options are here. Again, just yes or no.
It's no.
Okay, so your voice broke. Can you say it again?
It is not perfectly secure, right? Because
Say,
the possible outputs are 1 and 0, and we'll get 1 if and only if both are correct. Like both are true. Both inputs are true.
okay, so you are
In
saying
other
this is
cases, we'll get
perfectly
only
secure.
0. So, no, it is not perfectly secure. That's what I'm saying.
Okay, you are saying it's not perfectly secure. Exactly, yeah. So
Yeah,
you are
because
right.
you will get the output 1 if and only if the inputs are 1 and 1.
Right, so yeah,
Yeah.
you are right. The answer is no. And yeah, so I'll just say what you said now. Let me write it down. So first of all, recall that first let's recall one-time pad. So in the one-time pad, the key is chosen random from the key space, which in this case is 0, 1 to the end. And the ciphertext is just the XOR of the message and the key. So by C equals to M XOR K, I mean it's bitwise XOR. Okay, so this is the original runtime tag, and in the class we show that this is perfectly secure. Now over here, what we are doing is the following. So over here, C is obtained as follows. Ci is Mi and Ki. Now, for this scheme to be perfectly secure, we need that for all distributions on the message space, which in this case is just which in this case is just 0, 1 to the n, and all messages in the message space, hypertext space. So this is just the definition of perfect security. Okay, I haven't done anything new. So to show that if we want to show that the current scheme is perfectly secure, we need to show that it satisfies this condition. And over here, this condition should hold for all distributions on the message space. So let's fix the uniform distribution. That is for all messages, probability, this probability. Okay. Now let's see what goes wrong in this scheme. Oh, I don't have extra space. So okay, so let's see what goes wrong in this scheme. So let M be this. Or rather, yeah. Yeah, so let C be this. Mm. So let's suppose that C is 1 to the n. Then the message and the key both should be 1 to the n. Is this fine? Because we are using the AND operation. So if C is an all one string, then both M and K have to be the all one string, right? But in that case, probability that M is equal to, let's say, 0 to the n, over here it's n, 0 to the n, given C is equal to 1 to the n, is equal to 0, which is not equals to 1 over 2 to the n, which is not equals to probability M equals to n. So what we have shown is the following. There exists a distribution, namely the uniform distribution on the message space, and a, a message small m equals to 1, 0 to the n, and the ciphertext small c equals to 1 to the c, such that this this condition, probability n equals to m given c equals to c equals to probability n equals to m, is not satisfied, right? However, this condition is required for any scheme to be perfectly secure, and since this scheme does not satisfy this condition, this scheme cannot be perfectly secure. Is this fine? Okay, so if this is fine, let me move on to the next problem. The next problem is similar. So consider a variant of the one-time pad where instead of using the XOR of the 2 bits, we use the OR of the 2 bits. So over here, the ith bit of the ciphertext is obtained by taking the ith bit OR of the ith bit of the message and the OR of the ith bit of the message with the ith bit of the key. So is this version perfectly secure? This question is very similar to the previous one.
No, it is. It is similar to
Right.
the last one, right? Instead of
Right.
1, use 0.
Exactly. Yeah. So the answer is it is not secure, and the solution is pretty similar to the last one. So yeah, let me just quickly write it. Let C be 1 to the n. No, this time it should be 0 to the n. Yeah, so let C be 0 to the n. Then the message and the keyboard should be 0 to the n. But then again, probability that the message is 1 to the n given ciphertext is 0 to the n is equal to 0, which is not equals to 1 over 2 to the n. Again, we'll assume the uniform distribution, which is equals to probability m equals to 1 to the n. So again, this is also not secure. Okay, so now let's let's look at the next question, which just asks us what goes wrong with schemes 6 and 7. So with the schemes in problem 6 and 7, but why does one-time pad work? So what's the difference between these two schemes and the one-time pad?
Because the probability of getting 1 as an output is same there. It is 1 by 2 in 1 times pad. But here,
Okay. Yeah. So
hello?
yeah. Hello.
Yeah, it is because like when you're using one time pad, when you're using the operation XO, so in
Right.
those 4 different possible outputs, there are 2 different inputs and sorry, there are 4 different inputs and 2 different output with equal probability. But here it is not the
Right.
case.
Yeah. Exactly. So as you just said, let's say uh, let us pick K. Let's just look at instead of looking at the entire message, let's just look at one bit of the message. Okay. And let's just look at that bit of the key. So if that bit of the key were picked uniformly at random from 0, 1, then probability that the ith bit of the ciphertext, okay, yeah, let me write it like this. Then regardless of what message, what the message bit mi is, ci is 0 with probability half and 1 with probability. So ci however ci is mi and ki or mi or ki. Ci depends on mi. In particular, if mi is 0, then over then Ci is 0 in the first case. Mi is 1, then Ci is also 1 in the second case. So in this way, when we use AND or either the AND operation or the OR operation, the ciphertext can leak some information about the message. And that's why like those AND and OR operations are not secure, but the XOR operation is. Okay, so now let's look at the next problem. So the next problem is when using the one-time pad with key equals to 0 to the L, we have that the encryption of M, which is equals to K XOR M, is just M, right? So the message is sent in the clear. So it has therefore been suggested to modify one-time pad by only encrypting with non-zero keys. So the question is the modified scheme perfectly secure? Yes or no? So would anyone like to attempt this question? Okay, so just try guessing what.
No.
Okay,
Yes.
can so can you give me an intuitive reason why it's not true? Why this is not secure? Okay, so yeah, you are right. It's not secure, and let's see why. So again, let's assume distribution on the message space. Also, let the message and ciphertext be the same. Then probability that the message is M given ciphertext is C is the same as 0, right? Which is not equals to 1 over 2 to the N, which is not equals to probability that the message is M. So this scheme does not satisfy the definition of perfect security, and therefore this is not secure. Intuitively, what is happening is the following.
Why is it 0 probability of M equal to M such that C equal to C?
Okay, so over here we are not allowing the key 0 to DL, right? Okay, so when we do not allow the key 0 to DL, if message and ciphertext both are exactly the same, can C be M XOR K? K is not all zeros.
Okay,
So if
okay.
M and
I
C are
got
the
it.
same, right? C can't be K XOR M. So this probability is 0, right? Okay, can you mute? Someone has turned their microphone on. Can you mute yourself? There is,
Raja, please mute.
yeah, correct. Okay, so intuitively what's happening is that again, C leaks some information about them. In particular, C leaks the fact information that the message is not M. Sorry, the message is not C. And okay, so C leaking the fact that the message is not C might seem like a very small thing, but uh, there, so like this was one, but this has been used at least once to help break an encryption scheme. In particular, the encryption scheme that the Germans used during World War II, Enigma, had this property that no character could map to itself because it seemed natural, right? That if you map a character to itself, your scheme might not be secure. So they created a scheme in which a character could not map to itself, and it was one of the things that helped cryptographers, British cryptanalysts break that scheme. So disallowing 0 to the L as a key can have disastrous consequences. Okay, so now let's look at the next problem. So the next problem is, consider the following encryption scheme. Here the message space is 0 to 4 and the key generation algorithm chooses a random key from the key space, and over here the key space is 0 to 5. And what the encryption algorithm does is the following. Uh, it returns the sum of k and m modulo 5. And what the decryption scheme does is that it just it returns the difference of c and k again modulo 5. The question is this scheme perfectly secure? Like, would you like to guess? So, are there no guesses?
No, sir.
No, no.
Okay. Why? Can you just
Sir,
give me some
because
intuitive reason?
attacker can apply brute force technique.
No. Okay, by secure, I mean, so we are here, over here we are looking at perfect security, right? So we are not supposed to look at whether attacker can do brute force or not. Here we are supposed to look at whether this scheme satisfies the definition of perfect security or not, right? I mean, otherwise, any scheme whose message space and ciphertext space are small would be sorry, whose message space and key space are small can be brute force, right?
I think it is perfectly secure by the definition.
Okay, why? Like, can you just give me some intuitive
Because
reason?
it is same as the one-time pad, na?
It is almost the same
No,
as
no, no,
one
no,
time
no,
path.
no.
There is one
Okay.
difference. Can you spot that difference?
Modulo 5 is there, na? Modulo 2 is
No,
one.
no,
Modulo
over
2.
here. Okay, no, over here, modulo 5 makes sense because our message space is from 0 to 4, right? If I were to do one time pad for just one bit messages, then my message space would be 0 and 1, and in that case, modulo 2 makes sense, right?
Okay. Yeah.
So if the message space is 0 to 1, we do modulo 2. If the message space is 0 to 4, we do modulo 5. So modulo 5 is not a problem. There is some other problem. So what is the key space? It's 0 to 5, and what is the message space? It's 0 to 4. In one time tab, the key space and the message space are exactly the same, right?
Yes, yes.
Yeah, so in fact, yeah, so over here they are not the same. That is why this is not the same as one time tab. And in fact, this is also not perfectly secure. Okay, so the answer is no, this is not perfectly secure. And yeah, let's see why this is not perfectly secure. So again, as usual, we'll assume the uniform distribution. And the message space is in this case is 0 to 4. Now we'll also fix the message that MV0. Then what do we have? So if the message is 0, Yeah, so if the message is 0 and the key is also 0, then the ciphertext is 0. If the message is 0, key is 1, the ciphertext is 1, the key is 2, the ciphertext is 2, 3, 4, and if the message is 0, the ciphertext is 5, then the key, sorry, if the message is 0 and the key is 5, then the ciphertext would be 0 plus 5 modulo 5, which is 0, right? So, probability, so the probability that ciphertext is 0 given messages. So the probability that ciphertext is 0 given message is 0. Yeah, so now, so if the ciphertext is 0, then it is, yeah. So if the ciphertext is 0, the probability of the message being 0 is increases, right? Right. Okay, otherwise let me do it like this will be cleaner. So let's, in the first case, we have message equals to 0, and now let's look at the message equals to 1 case. Okay, let's draw the table. So if the message is 1 and the key is 0, this would be 1, 2, 3, 4, yeah, I miss a line, 4, oh, 0 and 1 again. So when the message is 0, this is 2 over 5, and this is 1 over 5, right? And these two are not the same. And recall that, like, one of the alternative definition of the of perfect security was that the ciphertext shouldn't depend. The probability that the ciphertext is a certain value should not depend on what the message is, right? So the that definition of perfect security says that these two quantities should be exactly the same, but they are not. So this scheme is not perfectly secure. This would have been perfectly secure if the key space was also 0 to the 4, 0 to 4, and we were going modulo 5. In that case, this would have been exactly like the one-time band. So is this fine? Okay, so if there is no question, let's move on to the next problem. Yeah. So the next problem is that we saw in the lecture that this game, private key with eavesdropper as an adversary and for scheme pi, gives an equivalent definition of perfect security. Now suppose that we modify this game as follows. Instead of the adversary sending messages M0 and M1, now the verifier picks messages M0 and M1 of their choice and sends them to the adversary. The question is, does the modify experiment also yield an equivalent definition of perfect security? Again, the options are yes or no. So, right. Would anyone like to guess? Or at least is the question clear? So earlier the adversary was picking two messages. Now the verifier can pick any two messages they want. So is the difference between the two scenarios clear? And if it is clear, like, would you like to guess what the answer is?
Can you please explain the question, Madhav? If you
Okay. Okay. So yeah. So let me just draw. So the game that we saw in class, or the experiment that we saw in class, was this. So that is this. We have an adversary, and we have a verifier. The adversary sends two messages. The adversary sends two messages to the verifier, and the verifier picks the uniformly at random from 0 and 1 and uses the key generation algorithm. Then it sends C is equal to we say that A succeeds, P prime and B are the same, and a scheme pi perfectly secure if probability that the adversary succeeds, that is B equals P prime, this is just half. So this is the experiment that we saw in the class, right? Now over here, the experiment that we have is slightly different. Over here, the experiment is as follows. So again, we have an adversary, and a challenger, a verifier. But now instead of the adversary sending them any two messages to the verifier can pick two messages, M0, M1 of their choice. Again, they pick a bit uniformly at random and a key, and they send and the verifier again the adversary succeeds if B prime and B are the same. Okay. So this is the experiment that we are considering in this question. The difference is that in the previous experiment, adversary was sending two messages. Now the verifier can send any two messages of their choice. And the question is the following. Uh, so here's the question. So now is the question clear?
Does it mean that encrypted messages and sent messages are same?
No, no, no. The, so so when you send the ciphertext, it's you apply the key on it, right? So it would be different. The ciphertext would be different. But now M0, M1, the verifier can choose any M0, M1 it wants. Okay, so the difference between the two is the following. in the first case, the adversary picks M0 and M1. So M0 and M1 are arbitrary, right? However, in the second case, the verifier picks M0 and M1. So since the verifier wants the adversary to fail, it can pick M0 and M1, which are very good, right? So in the second case, M0 and M1 need not be arbitrary, right? That's the difference. So is the question clear?
Yes, sir.
Yes, sir.
Okay. So now, like, what do you think? Would this scheme also be perfectly secure? Like, would this be perfectly secure? If you were to define a scheme by saying that if the adversary only succeeds in this new experiment with probability half, then the scheme is secure.
Yes.
Okay, why?
Because to have a means if if the probability was more than 1 by 2, then it was not secure. But
Okay, okay. So the answer is it's actually not secure. It actually won't be secure, and here's the reason. So yeah. Now observe that it's in the verifier's hand to send M0 and M1, right? Not the adversary's hand. So what the verifier can do is the following. Let's say 0 to the L minus 1 and 0 and 0 to the L minus 1 or 1 to the L minus 1 and 0. Also suppose that the encryption algorithm does the following. So it XORs this string as the encryption scheme does this. If the last bit so if the last bit of M is 1, then it does something very stupid. So is the scheme clear? So what the scheme does is that if the last bit of the message is 0, then it just applies the one-time pad on the first L minus 1 bit. Then it just applies the one-time pad. But if the last bit is 1, then it just sends the message as it is. So clearly this scheme is not secure, right? The scheme that I've written over here. However, since it is in the hand of the verifier to send messages M0 and M1, here's how the verifier can win the game. It sends M0 and M1, both of whose last bits are 0, right? Now, whenever the last bit is 0, this scheme is just like the one-time pad. So if M0 and M1 both have last bit 0, then the adversary can only succeed with probability half. Right. So the problem with this experiment is that the verifier can pick two messages to send, and it is possible that your scheme is secure only for some messages in your message space, not all messages in your message space. And what the verifier does is that it just picks those messages, M0 and M1, for which the scheme is secure. So is this fine? Or should I explain some part of this again? Okay, so if no one has any questions, we can move to the next problem. Okay, so the next problem is which of the following is or are the limitations of perfect security? The options are the key should be at least as large as the message. No perfectly secure encryption schemes exist. So perfect secure. So that yeah. So perfect security is not a useful definition. The key cannot be reused for subsequent messages, and for all known perfectly secure encryption schemes, the encryption algorithm itself takes exponential time. So it's too costly to use perfectly secure encryption schemes. This is just a recall question. We saw this in class. So does anyone of you want to answer this question?
Sorry, A, B,
A
C.
and C,
A, yeah.
A and C.
Okay, so one person said B and C, another person said A, another person said A and C. Yeah, so the answers are A and C. The key should be at least as large as the message, and the key cannot be reused. And we saw this in class. The next problem is as follows. Consider the following variant of the shift cipher. So let M be the message M1 to ML. Then for all I in L, we pick Ki uniformly at random from 0 to 25 and shift Mi by K places if wrap around if necessary. So for example, let's say M1 was Z and we picked 25, then we would get Z plus Z. That would exceed Z, so we'll just wrap around. So is this cipher perfectly secure? Is the question clear?
No, it is not, right? If it is of finite length, it is not.
Okay, can you repeat the answer? Your voice broke.
It is
At least
not,
for
right?
me. Okay, and what's the reason?
If it is of finite length, it is not, I think.
Okay,
Because by brute force attack, we can find it, right?
okay. So over here, L is some arbitrary number. It can be as large as you want.
Oh, okay.
Okay, so yeah, so okay, so let me just tell you the answer. The answer is that this scheme is perfectly secure, and here's the reason. In fact, this is exactly the one-time pad scheme. So the answer is that this is with message space 0 to 25 to the L, and the key space is also 0 to 25 to the L. Okay, so the message is going to be a string of alphabets, but you can map A to 0, B to 1, and so on, Z to 25. So we can just assume that and key, the message and the key are both lie in this 0, 25 to the L. And what are we doing? So we are picking key uniformly at random from so this is exactly the one-time pad for with these as message and key space. So this is perfectly secure. Is this fine? Okay, so let's move to the next problem then. So is the following statement true or false? For any cipher or any encryption scheme to have perfect security, it must have the following property. For all distributions on the message space and the key space, as well as for all ciphertext C1, C2 and message M, probability that the ciphertext is C1 given message is M is the same as the probability that ciphertext is C2 given the message is M. So would you like to guess whether this is true or false? Like, I mean, you can just guess anything. Okay, so
False.
yeah, okay. Then do you have some intuition why this is false?
Because it doesn't depend on ciphertext mainly. It depends on plain text.
Okay, what depends on plain text? Oh, are you saying that if the
Definition of perfect
okay, so
security.
okay, so what you are saying is if the roles of M and C were reversed, then this would be perfectly secure. Is that what you are saying?
Yes, sir. Yes, sir.
Okay, yeah. Okay, so but
This
we
won't
still
happen unless it's a random algorithm, right? Randomized algorithm, that encryption scheme. If it is a
okay.
deterministic algorithm, then the probability of C is equal to C1 such that M is equal to M won't be equal to the other one, right?
No. Okay. So what do these two probabilities depend on? They depend on the key, right? What the key is. So what the first property is saying is, so okay, these properties over here are over the choice, the random choice of the key, right?
Yes, yes.
Okay. So what this is saying is that it's equally likely that you will find some key which maps M to C1 and M to C2. So is this a necessary property for some uh, a perfectly secure scheme to have? Okay, so you were right. The answer is no, and let me show you why. So what we'll do is we'll construct a scheme which is perfectly secure but which does not have this property. Okay. So what we are going to do is this. So here's what the encryption algorithm does. So far it's just like one-time pad, but then it outputs. So here's an example of a scheme where this property does not hold, right? So what we are going to do is we are going to take the message and key space are just going to be 0 to the L. However, the ciphertext has one extra bit. And what the encryption algorithm does is, in this case, it's randomized and it first of all XORs the message and the key, but then appends 0 with probably 2/3 and appends 1 with probably 1/3. Okay. And what the decryption algorithm would do is it would just ignore the last bit and look at the first L bits. Okay. So is the scheme clear? Now this scheme is perfectly secure. To a one-time pad with message space, key space, text. So what I'm claiming is that this scheme is equivalent to a one-time pad scheme where the message space, key space, and hypertext space all are 0, 1 to the L. And the reason is short. The ciphertext has one extra bit, but that extra bit does not reveal any information about M. In fact, it's independent of everything. It's just some padding, right? So this scheme is perfectly secure. However, probability that the ciphertext is, let's say, 0 to the L plus 1 given messages n for any message n is so this is greater than so is this clear? Why? Because uh, because the encryption scheme appends the last bit 0 with much more probability than it appends the last bit 1. So the two properties are not the same. However, the encryption scheme is still secure. Okay. So now let's look at the question again. The question was asking whether these two probabilities must be the same for every secure encryption scheme, right? But we just showed that there exists an encryption scheme which is perfectly secure, but which does not have that property, right? So the statement is false. Is this fine? Yeah, so then if it is, let's move on to the next problem. So the next problem is the following. So suppose the ciphertext is don't panic with no spaces, and we want to encrypt this using the Wigner cipher and the key toggle. So what is the encryption of this uh, using this key? So now, okay, I won't ask you what the answer is because yeah, this needs to be worked out. But let's work this out. Okay. Okay. So what do we do? Okay. So can someone tell me what Wigner cipher does? We saw this in class.
It will divide the whole plain text into uh, tests of particular length first using
Okay.
that whatever key you have. Here it is tablet,
Right.
so it
Right.
is of 5 character length, so it will divide it into particular tests with 5 characters, and then we'll each
Okay.
one will use a key to like find the cipher test for each one. Use the
Okay.
cipher. Yeah, we'll find the cipher test
Right.
using each one.
Okay. So as you said, let's just first divide this into 5 parts. So this is the first part. Let me write the second part a little fast. Okay. Now what we'll do, we'll write the key underneath it, right? And now we'll just add these two up. So for that, we need the numerical values of these numbers, and let's just assume that a maps to 0. So now, okay, now it's very simple. You guys should tell me what I should write over here. What I want to do is I want to convert these numbers into, sorry, these letters into numbers. And A would go to 0, B would go to 1, and so on. So what should I write for don't panic? What number should I write for don't panic?
0, 15, 14.
Wait, why is D 0?
Sorry, not D is 4. Sorry.
Okay, D is 3, right? Because A is 0, so D is 3.
Yeah.
Okay,
Yeah. Okay. Sorry. Yeah.
right. Uh, what about O?
Then O is 14.
Okay,
N is 13.
right.
And
T
T is
is
19, I think.
right.
And A is 0.
Oh, there is P over here. P is 15.
Yeah. Okay. Sorry.
Then A is 0. N we saw is 13.
It's
What is
20.
I?
It's
I
8.
is right. And C is 2. Right.
C is 2.
T we saw is 19. O we saw is 14. N W is
Is it 21?
wait.
it 21 or 22? It's 22.
Yeah, it's
Sorry,
22.
21.
Okay.
It's 22. It's
Yeah,
23rd
it's
letter.
20. Yeah, it's 22. E is 4. L is
12. Sorry, 11. It's
yeah,
the
L is
12th letter.
11,
So
right? Yeah, 11. Again, now we'll just wrap around. So 19, 14, 22, 4. Now we are just supposed to add these up. So it's 19, 22, 22, 28, which modulo 26 becomes 2. 13 plus 22 is 35. Again, modulo 26, this becomes 9. This is 23. This is 36, which modulo 26 becomes 10, 19, 27. Modulo 26 is 1. Again, 30. This is 4 and 6. Okay, so now we need to do the reverse process. What's the 22nd
Sir,
letter?
15 by 11 is 26. 26
Oh, yeah,
modulo
sorry.
26
So,
0.
yeah, right.
It
Yeah,
will come 0.
yeah. Okay, so now what's the 22nd letter? It's W. Yeah. What's the second? It's C. Ninth is 10, so it's J. 23rd is,
X.
yeah, X, right, because it's 24th. And 26 is 0, so A. 19 is, we saw where T. E, third is, yeah, G. So, yeah, so it's this. And now the reason that we recalled this and how this example is the following question. And so the question is the following. Suppose that we have a 1,000-character message which contains the phrase attack at dawn twice. The first starting from position 42 and the second starting from position 954. Now assume that this message, the entire 1,000-character message, is encrypted using Figner cipher. And also assume that the key length is n and all the characters of the key are distinct. Then for which values of the key length will both the occurrences of the encrypted ciphertext, so that is for which key lengths will both the occurrences of attack at dawn be encrypted to the same ciphertext. So is the question clear? Okay, so so if the question is clear, would you uh, would you like to guess, or does anyone have a candidate approach to solve this problem? Okay, how should we approach this problem?
One thing we can say is actually the key length should divide the difference between that 954 and
Exactly,
52, right?
yeah, that's the answer. So the key length n should be a
But
factor of
it could be
912.
any number, right? We'll get multiple number, right?
Yeah. So the question is then for which values of the key length will both the occurrences be the same? So the answer is whenever the key length is a factor of 912, that would work, right? Any factor of 912 would do.
Yes.
912 is just a difference. Okay, so yeah. So the answer is just this. Let me just write this down. So suppose that the 42nd character using the ith 10, since the characters of the key are distinct, the characters of the key. The 954th character should also be encrypted. Any j such that the jth character is encrypted using the ith bit ki as the form size of k, the size of the key, times n plus 42 for some natural number n, right? So is this claim fine that any character which is encrypted using the ith bit must have this form? It must be this character. Why? Because the first character is 42. The second character would be 42 plus the size of the key. The third character would be 42 plus 2 times the size of the key and so on. So this means that 954 is equal to size of k times n plus 52, which is the same as 912 equals to size of k plus size of k times n. And which implies that size of k must divide 91. Okay, so in this question, uh, the, all the characters of the key were distinct. Okay, so what if like some characters in the key are repeated? In that case, would this answer still be complete? Or like, can there be multiple values of, can there be some other values of n for which this would also happen? So is the question clear?
If the characters in the key are not distinct, it can happen, right?
Right. For example, here's a very simple
If it
example.
is
Let's say
repeated.
let's say the length of the key is 22,000. Okay. But each and every character in the key is the same. Let's say A. Then attack. Then every time this phrase appears, no matter where it appears, it would always be encrypted with the same ciphertext, right? So if the characters in the key are the same, then we cannot say that these are the only possible values of n for which this is true. Yeah, and I used n over here again for some different context. Like me just replace this with n. Yeah. So if this is fine, let's move on to the next problem. Okay, so the next problem is this is a very cute problem. In the movie Imitation Game, Alan Turing and his fellow cryptanalysts crucially used the information that every German message ended with the phrase Heil Hitler to break the enigma. So which of the following best describes the attack model that they used? Ciphertext only attack, known plaintext attack, chosen plaintext attack, or chosen ciphertext attack? So which of these four was the attack model that they used? And okay,
Chosen ciphertext.
okay, that was too loud. Can you lower your volume a
Sorry,
little? Yeah. So can you lower your volume a little and say that again?
chosen ciphertext attack.
Okay, so why is this a chosen ciphertext attack? Because that in the chosen ciphertext attack, the attacker can gain access to message ciphertext pair for the chosen ciphertext, right?
The ciphertext only attack, right?
Okay, but there has some extra information, right? So okay, first of all, let me tell you why this is not the chosen ciphertext attack. Over here, they had no they they weren't able to ask the Germans to decrypt some ciphertext for them, right?
Okay, then it's ciphertext only attack.
Okay, so over here they did know that this phrase Heil Hitler would appear, but this phrase Heil Hitler was not of their choosing, right? If it were of their choosing, then this would have been a chosen hypertext attack. Okay, now this is also not only the chosen, this is also not just this ciphertext only attack, because in that case they wouldn't even know that Heil Hitler appears in the ciphertext, right? They would have no information about the cipher, no information about what appears in the ciphertext, right? So A and D are not correct. So now we are left with B and C. So which of these is the model?
Is it chosen plain text attack because since he knows Heil Hitler, he can get the decrypted version of that particular word.
Okay, again,
So
what
he may
happens
play.
right? Yeah, so what happens in the chosen plaintext attack? The attacker is able to get ciphertexts, but the attacker is able to get message ciphertext pairs, but for plaintext of their choosing, right? So over here, the phrase Heil Hitler is not of their choosing, right? It's just some phrase that they know occurs, right? So the answer is the known plaintext attack. They just knew that this plaintext, Heil Hitler, appears at the end of the message. So to obtain the message ciphertext pair, they had to just look at the end of the message, right? So
It is ciphertext, na? Hitler is a ciphertext or plain text?
no, okay. Heil Hitler is a plain text. It just means hail to Hitler. It's a plain text, and they knew that every German message ended with this phrase. So when you encrypt it, you would get the encrypted version of Heil Hitler in the encrypted message.
Okay, then it is a known plain text attack.
Right. Yeah. So it's not chosen plaintext attack because Heil Hitler was not of their choosing. Yeah. If it was some phrase of their choosing, it would have been a chosen plaintext attack. Okay, so the next problem is somewhat similar, and this is also based on a true event. So during World War II, the American cryptanalysts used the following strategy to break a certain Japanese cipher. They sent the message, Midway is out of drinking water, in plain text, knowing that the nearby Japanese listening station would intercept this message, encrypt it, and then forward it to their headquarters. Now, after that, what the Americans would do is the following. The American listening station would intercept this encrypted message that the Japanese just sent, And then this session would send this to the cryptanalysts, and the cryptanalysts would use this encrypted message to help them break the cipher. So, which of the following best describes the attack model used by the Americans? Chosen ciphertext only attack, known plaintext attack, chosen plaintext attack, or chosen ciphertext attack? So, is the situation over here clear? So, over here, the Americans were able to send a message of their choosing to the Japanese and get a ciphertext for that message. So, which attack model did they use? This is somewhat similar to the previous question. Okay, so if there are no guesses, the answer is chosen plaintext attack, because over here they were able to get a message hypertext pair, sure, but the message was of their choosing, midway out of drinking water. So this is just not the known plaintext attack, it's a chosen plaintext attack. Is this fine? Okay, so we have 15 minutes left. So in the last 15 minutes, if any of you has any doubts from what was covered during this week, you can ask me. Otherwise, if no one has any doubts, we can move on to the next week. We have some more problems, we can solve them. So I'll wait for a minute or two to see if someone has a question. Otherwise, we'll move on.
How to check if a function is negligible or not?
Okay, so the definition of the negligible function is the following, right? It's small. It's smaller than an inverse polynomial function, right?
Yes.
Yeah. So, like, what do you mean that you want to check whether a function is negligible or not? Here is one way to do it. Okay. So, how are you given a function? Are you given its formula, or are you given a graph of that function?
Formula.
Okay. So, if you are given a formula, just come. Okay. So, does the formula look like 1 over some function? Let's say the function you have in hand is f of n. Does that formula look like 1 over g of n?
No, it's like f of x is equals to 2 power minus n, or f of x is equals to 2 power minus square root of n, something.
Okay, right. So, okay, first of all, if your function is 2 power minus n or 2 power minus square root n, it is actually of the form 1 over g to the n, right? G of n,
Yeah.
right? Because 2 to the minus n is just 1 over 2 to the n, right? Yeah, so whenever your function is of the form 1 over gn for some function gn, just check if gn is asymptotically larger than like a polynomial function. Because if gn is super polynomial, then 1 over gn would be smaller than the inverse of a polynomial function, right?
Yeah.
Yeah, so that's the way to check if your function is negligible or not. If you are given if your function is given like 1 over g of n. Otherwise, if you are given the values of the function at some points, like plot a graph and see, okay, and see the inverse of that function. So let's say you are given a function f at some points, let's say 1 to 1,000, okay. Then what you should do is you should plot 1 over f of n and see if that plot is a super polynomial plot or not. So basically, look at the inverse of the function. That should be super polynomial in either case, whether you are given an explicit formula for the function, or you are given a graph of a function, or you are given the function at a bunch of points. Yeah. So are there any other questions?
In the 6 to 8 meeting, the same question will be discussed.
I don't think so. I think the first 5 or so questions might be the same. The next, I don't think would be.
What they will discuss in 6 to 8?
Okay, so the PAs are different, so I don't know. The thing would be similar, so there would again be problems.
For
But
week
yeah, I
one only,
don't.
na? For week one only.
Yes, for week one only. So okay, what's basically going to happen is there are 3 sessions. In all 3 sessions, problems related to week one would be discussed. But some of the problems would be similar, some might not be.
Okay.
Yeah. So, does anyone else have some other questions, or otherwise we can solve some more problems?
Yes, please.
Yeah. Okay, so let's move on to the next problem. The problem is as follows. Alice wants to communicate securely with Bob, so she has come up with the following cipher. They agree on a key picked randomly from 0, 1 to the L, picked uniformly and randomly from 0, 1 to the L beforehand. Then, for a message M in 0, 1 to the okay, wait. So the message should be in 0, 1 to the 2L. The typo. This should be 2L. Then for a message in 0, 1 to the 2L, Alice does the following. She uses the key to encrypt the first L bits of the message using one-time path. Then she picks a K prime uniformly at random from 0, 1 to the L and uses the complement of K, that is K with its bits flipped, to send K prime to Bob using OTP. Again, one-time path. And finally, she uses K prime to encrypt the remaining L bits of M using one-time path. So question is the cipher secure or not? So what is happening is Alice wants to send a message of length 2M, 2L. She first sends the first half with one key, then uses that key to send the second part of the key, and then uses the second part of the key to encrypt the second part of the message. And the question is the cipher secure or perfectly secure or not? So this cipher does bear some resemblance to one-time path, but is it secure? Okay, so over here, is the key length the same as the message length? Or is the key length less than the message length? Okay, the message length is
It's
2L.
less.
Yeah, the message length is 2L, the key length is L, right? So can an encryption scheme where the key length is smaller than the message length be perfectly secure? I mean, this we have seen in the class, right?
It's not secure.
Yeah. So the answer is it's not secure. Yeah, so the answer is it's not secure. Okay, so now what we'll do is the following. So we saw 3 equivalent definitions of perfect security, right? What we'll do is that we'll show that one of this encryption scheme does not satisfy one of those definitions. So in the previous problems, we have used the first definition. We have used the second definition. So far, we have not used the third definition, right? Where there is an adversary, there is a verifier, the adversary, and verifier performs an experiment. Okay. So what we'll do is we'll use that definition to prove that this is not secure. Okay. So here's how we're going to do it. So, okay, first of all, notice the following. Suppose that so suppose that our message looked like M1, M2, where M1 is all zeros and M2 is any arbitrary L bit string. Okay. Then what will happen when we encrypt this message using the encryption scheme? Then if Alice sends C1 is equal to M1 XOR K is equal to just K, C2 is equal to K, sorry, M2. So is this clear? So if the message looked like 0 to the L and M2, then just looking at C1, C2, and C3, the ciphertext that Alice sends to Bob, we would be able to figure out what M2 is. Is this clear? And if it is clear, can someone tell me how can we do this? Or why can we do this? Okay, so the reason is the following. What is C1? C1 is just K because M1 is 0 to the N. So from C2, we can find out K prime as follows. K prime is K bar XOR C2. Now we know K, so we can flip the bits of K to obtain K bar, XOR it with C2. Now we have K prime. And what is M2? M2 is just C3 XOR K, K prime. So we can find out what M2 is, and therefore what the entire message M is, it's 0 to the L M2, if M were of this specific form, right? And what we'll do is we'll use this to create two messages M0, M1 in that game for and show that the adversary can succeed with a very high probability. Okay. So here's what we are going to do. So this is the adversary. And this is the verifier. The adversary will send these two messages, 0 to the L, 0 to the L, and 0 to the L, 1 to the L. Then the verifier would send C1, C2, and C3. Okay, no, first the verifier would pick a bit uniformly at random from 0, 1 to the from 0, 1 and send C1, C2, C3. It will do this. It will pick K uniformly at random, K prime uniformly at random from 0, 1 to the L, and then it would send C1, C2, and C3 obtained by encrypting using K and K prime. The message, okay, let me call this M0. Let me call this M0 prime. Right. Now, what the adversary will do is the following. As we saw before, Since both n0 prime and n1 prime is 0 to the L as their first L bits, the adversary would be able to find out whether the last L bits are 0 to the L or 1 to the L, right? Using what we saw in the previous slide. So if the last L bits B prime is 0, otherwise 1 to the L, B prime is 1. So in this case, the probability that B equals to B prime, this is 1, which is greater than half, and so the scheme is not secure. So is this fine? So if no one has any questions, let's move on to the next problem. This being okay. So this is a long problem. So let's move to the next one. Okay, yeah. So consider a cipher pi in which the message space, the key space, and the ciphertext space are all. The ciphertext is obtained by just XORing the message and the key. Okay. Now the question is the following: is a key generation algorithm doesn't pick keys uniformly at random from 0, 1 to the L, is pi perfectly secure? So we are using an encryption scheme which is very similar to the one-time pad. However, we are asking, what if the key generation algorithm does not pick keys uniformly at random? Would that version of one-time pad still be perfectly secure? So would you like to guess what the answer is? It's pretty simple. Okay, so the answer is no, and the reason is very simple. So it can just output some fixed key, let's say 0 to the L. Then message and ciphertext would be the same, and yeah, we will be sending the message in as plain text. So if in one time that we don't pick keys uniformly at random from the key space, but use some other distribution, like for example here we are using a point mass distribution, then that version of one-time pad might not be secure. Yeah. So yeah, let's just end today. If you don't have any questions, we can continue next time. And next time we'll discuss problems for week 2. Okay, so if no one else has any questions, thank you for sitting through this session. Bye.